All right, guys, I'm so glad you are here. Welcome to the super exciting lesson on Maclaurin Series. All right, so in our last video, we learned how to write some series or some functions as a polynomial series. But that's kind of boring, right? It had to be kind of close to 1 over 1 minus x. What we want is a strategy to write any function, no matter what, as an infinite polynomial series. And that's what Maclaurin Series is going to let you do. And our goal is to figure out how. So if we wanted to write some series, thinking about this, so we would write it as, some a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3x cubed plus a sub 4x to the 4, and so on. And then I'd have some general term a sub n times x to the n. So our goal that we're going to try and do is we're going to try and find these constants a sub n and find some kind of pattern. So these are all constants, and our goal is to figure out what those constants are. And the way we're going to do this is by using derivatives. So let me take a look at what that looks like. So we talked about how to find a derivative of a series. So let's go ahead and do that. So if we take the derivatives, remember all these a sub n, and if we say a sub 3 is just like the x to the 3 constants. What's the constant on the x to the 3 term? And our goal is to figure out what those constants are. So when we take a derivative, the derivative of the a sub 0, of course, is just 0. It's a constant. When I take a derivative of a sub 1 times x, I take the derivative of 3x, that's 3. So derivative of a sub 1 times x is just a sub 1. When I take a derivative of a sub 2 times x, the 2 comes down, right? So it's like 2 times a sub 2x. Okay, and the next one, the 3 comes down, so it's 3 times a sub 3x squared. The next one, the 4 comes down, so that's 4 a sub 4x cubed. And as to the general term, remember a sub n is a constant, so we bring the n in front. It's like n times a sub n times x to the n minus 1. Okay, so let's take a couple more derivatives. And remember, our goal is to find these constants, and hopefully we're going to figure out a pattern for what these constants are. And spoiler alert, we are going to. Okay, so let's take a second derivative. So if I take a second derivative of this, derivative of a sub 1 goes to 0. Then derivative of constant times x is 2a sub 2. On the next one, 2 comes down, so 3 times 2 times a sub 3 times x, plus, and then 4 times 3 times a sub 4x squared. Okay, and then so forth here. And then when we go a little bit further here, we'll go one more, the third derivative. The first one again is a constant. Here we have 3 times 2 times a sub 3x, and then we have 4 times 3 times 2 a sub 4x. I'm just not multiplying this out because I'm lazy, or maybe there's an alternative motive. We'll find out. Okay, so these are the series for f prime, f double prime, f triple prime. And remember that our goal was to find the constants. We wanted to find the value of a sub 0, a sub 1, a sub 2, and so forth. And hopefully identify a pattern. So what I'm going to do is I'm going to take these equations for f prime, f double prime, f triple prime, and I'm going to plug in 0. So let's go down here. So when I have this f of x, f of 0 is equal to a sub 0 plus, and then, the next term is 0 because it's got an x. We're plugging in x is 0. And then the next term has a 0x squared, that's 0. Well, all the other terms are 0. So my f of 0 is just a sub 0. That's the first constant right there. Great. Okay, well, let's plug in the the f single prime equation. So f prime of 0 is a sub 1 plus 0. Oh my goodness, those are all 0 too. So my f prime of 0 is just the same as a sub 1, the x coefficient. Well, let's keep going with the second equation. So f double prime is 0, if I plug in, is 2 times a sub 2, and again, everything else is 0. So if I wanted to solve for a sub 2, that'd be easy. I could just divide over and get the second derivative divided by 2. Okay, now when I go one further step, when I plug in the third derivative here, the third derivative at 0. So that's 3 times 2. Oh, well, I screwed that up. That's nice. I left off the x there, my bad. So when I do that, that's 3 times 2 times a sub 3. So when I solve, my a sub 3 is equal to the third derivative at 0 divided by 3 times 2. Now I want to think about this. Is there another way I could write 3 times 2? Well, you might say 6, and you're not wrong, but the better answer is 3 factorial, right? 3 times 2 times 1 is just 6. So you can write the third coefficient as the third derivative over 3 factorial. And that's actually true on all these, right? The second coefficient is the second derivative over 2 factorial. The first one is over 1 factorial. The 0th one's even over 0 factorial because 0 factorial is just 1. So what we have is my pattern is that if I want to find that x to the nth coefficient, that a sub n, is equal to the nth derivative at 0 divided by n factorial. That is the pattern, and that's how we can find those constants. And this is true for any function. This is just saying that if you want to find that x to the nth coefficient on this series, which is called a Maclaurin series, you just take the nth derivative at 0 and divide by n factorial. And if you want to see where that comes from, right, if you take the derivative of x to the fifth over and over, you get 5x to the 4, and then 5 times 4, x cubed, and then 5 times 4 times 3, x squared. That's where the factorial comes from. When you take repeated derivatives, you just keep multiplying by those powers. Great, so that's the key pattern here. Awesome. So what that means is, if I go back, so my Maclaurin series looked like this. This f of x originally, let's go back, we just started with this. We said, here's my Maclaurin series, it looks like this. This a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed. And then my general term of that series was a sub n times x to the n. All I'm going to do is I'm just going to take these results right here and I'm going to plug them in. So this is my a sub 3, my a sub 2, my a sub 0, my a sub 1, and I'm going to plug those in. So I'm going to plug in those formulas we just got for the constants. And that allows us to write our function as, okay, a sub 0 is f of 0 plus a sub 1 is f prime of 0 times x. And then we have f double prime of 0 over 2 factorial, x squared. 2 factorial is just 2, of course. Don't get confused on that. And the third derivative is 0 over 3 factorial, x cubed. And then my general term, just kind of saying what the nth term of the series is, was the nth derivative, which you just write in parentheses like that. So it's not an exponent. The nth derivative is 0 over n factorial times x to the n. And this, my friends, is the all-important, all-powerful Maclaurin series. Wow. So what that's saying, and the key insight on this, is if you have the derivatives at 0 are enough to give you the equation for the series. Because this is the same for any function f of x. As long as you can figure out what are these values of the derivatives, you could just plug those in, and that'll let you write any function as a series. Extremely powerful. Think of those derivatives at 0 as the DNA, right? Those are the DNA in the middle of the cell that gives you the entire body of the infinite series. As long as you have those derivatives at 0, that DNA, it gives you the whole series. Okay, cool. So that's a big idea. Let's do some example problems here. Let's say we have the first 4 terms in the Maclaurin series we're trying to find, and I give you these derivatives right here. And the great thing is that if you have the derivatives, all you need to do is just plug those chumps in. So that tells you that you can write f of x equals, and then just plug those guys into the series. Those are the first 4 terms, 1, 2, 3, 4. Just literally count to 4. So when I plug in that first derivative, that was 12. So 12 plus first derivative, so 3x. My second derivative, 0. That just worked out nicely. So 0x squared over 2 factorial. My third derivative was negative 3 over 3 factorial times x cubed. Okay, and there we go. Those are the first 4 terms of the series. You can clean it up a little, but those are the first 4 terms of your series as long as you're given those derivatives. Great. Okay, let's get to something cool. Let's get to how we can write cosine as a series. And that's what we're going to do for this last kind of example here. So how can we write cosine x and find the Maclaurin series, the special series, to write cosine x as a series? And the way we're going to do it is using this formula. This is the key formula for this entire assignment and basically this whole chapter. Basically what we're going to do is we're going to find the derivatives at 0, and then we're going to plug those in. So we're going to find the derivatives of 0, plug into that equation, which I just boxed. Okay, so we're going to start by just taking some derivatives of cosine x. So when we want to find the 0th derivative, that's just the original function, right? So the 0th derivative, just the original function, is cosine of 0, which all the cool kids know is 1. The first derivative is negative sine of x. So when I take the derivative g prime is 0, that's negative sine of 0, which is 0. Okay, the second derivative of negative sine, is negative cosine. So when I do the second derivative, I'm going to go ahead and just do the negative cosine of 0, which of course is negative 1. When I do my third derivative, I get to a positive sine of x. So the third derivative is 0, of course, is the sine of 0, which is 0. And then when I take the fourth derivative, which sometimes you just write in parentheses like that, the fourth derivative is back to cosine x. So that's where the pattern is going to come from. So if I take the fourth derivative, I'm back to 1. Because now when I see the fifth derivative, which again is right in parentheses, I can back to negative sine, and my fifth derivative is just going to be 0. So we can see this pattern, right? 1, 0, negative 1, 0, 1, 0, negative 1, 0, and so forth. Okay, great. So now what I'm going to do is I'm going to take the derivatives and I'm going to plug in the derivatives into this equation. And this is going to allow me to write cosine x as a series. Again, going back to this equation right here. So I'm going to say that cosine x equals, okay, so I do my f of 0 plus f prime of 0 times x plus f double prime of 0, x squared over 2 factorial, and so forth. So when I plug those in, I'm going to get 1, and then we have a 0x, and then the second derivative is negative 2. So I'm going to have negative 1. So I'm going to get a negative 1 x squared over 2 factorial. And then I'm going to go a 0 x cubed. My fourth derivative is positive 1, so plus 1 x to the 4 over 4 factorial. And then my next one was a 0 x to the 5th. My next one was, it was negative 1 x to the 6 over 6 factorial. Okay, so let's clean this up. And I'm always going to tell you how many series to write. When I tell you to write a series, here they tell you 4 non-zero terms in general term. We have 1, 2, 3, 4 terms that are not 0. So let's go ahead. So let's write this out. So we have 1 minus x squared over 2 factorial plus the next non-zero term x to the 4 over 4 factorial minus x to the 6 over 6 factorial. Okay, and now what I'd like us to do is to also write not just the first couple terms, but also the general term, meaning it's going to be in terms of n. So how do we find the next term in the series? What's the formula, basically? Well, let's see. Let's see if we can put this together. First off, this is an alternating series, right? It goes plus, minus, plus, minus. So because it's alternating, we're going to have a negative 1 to the n. Okay. And then let's see, what else do we recognize? Well, it's only the even power terms, right? We have x squared, x to the 4, x to the 6. So a tip I want to give you is if you have even power terms, you're going to use 2n, right? Because n goes 1, 2, 3, 4, 2n goes 2, 4, 6, 8. It's all the even numbers. If you have the odd powers, just use 2n plus 1. Because if n goes 0, 1, 2, 3, your 2n plus 1 goes 1, 3, 5, 7. So that's how you can get the even versus the odd. Okay, so now I'm going to write the general term. I see that all my exponents that I have in here are the even ones. I have 2, 4, 6. So I'm going to have an x to the 2n. Okay, and then I notice, the factorial always just matches the exponent, right? 4 over 4 factorial, 6 over 6 factorial. So that's going to be a 2n over a 2n factorial. Okay, so hopefully you see where that comes from, but this is the Maclaurin series for cosine x. And I can't represent enough how important this is. This is how you can write cosine x as an infinite polynomial series. This is cosine x. It's just another way to write cosine x. When your calculator finds cosine x, all it does is just plug the number into the first 10 or 20 terms of the series. That's how it actually calculates the cosine or the sine or the tangent of some number, is it uses something like a Maclaurin series. Wow. Huge. And again, I want to show you on the calculator what happens if you graph this. So here's cosine, and what you'll see is if you type in just more and more terms, it's going to get more and more accurate. So here's x squared over 2 factorial plus, and then, go back. Okay, and then plus x to the 4th power divided by 4 factorial, which is 20. Oh, God, no. Why is it doing this? X to the 4, okay, and then divided, oh God, no, it's so bad. Okay. It doesn't like that I didn't finish the fraction. Let's clean that up a little bit. Okay, sorry. Plus, and then we have x to the 4th power divided, oh no, you bastard. Okay, x to the 4th power divided by 24. And then the next term of the series is minus. And then we have x to the 6th power. And then we're dividing that by 720, which is 6 factorial. So what you see is the more terms you add, the closer and closer it gets. And you can see that if we look just in here, these, even just the first 4 terms of the series, almost exactly match cosine x. And what you'll see is the more and more terms you add, the closer a match you have, and the wider it goes. So this series, again, is just another way to write cosine x. And if you have a couple terms as an estimate, but the more terms you write, it really is just a perfect match for it. Okay, so one other thing really that I wanted to talk about is the difference between equals and approximate. Those are important. You use an equal sign when you have an infinite amount. If you have an infinite series. So cosine x equals 1 minus x squared over 2 factorial plus x to the 4 over 4. And by the way, you will need to memorize the series at some point. So you might as well start now. It's just the even powers and alternates. Cosine x equals this series. But if you just look at the first couple terms, cosine x is just approximately 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. So if I just have no dot 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 at the end, it's just an approximation. If I actually have all infinite terms, because this is not just 3 terms, but all infinite terms, it is a true equal sign. Cosine x is equal to that infinite Maclaurin series. Okay, wow, big ideas in here, guys. Thanks so much for watching. Hope you got a lot out of this. I'm sure you got questions. Make sure you bring them to class. And then also, go ahead and start this. Try and do the same thing we did, and try and write the Maclaurin series for sine of x, just like we did for cosine in this video. All right, thank you all for watching. I'll see you guys soon.